What's up, guys? The Immortal Nerd here, and welcome to Let's Talk Calculus. Yes, this is a new theme, I guess you can say, or segment, whatever talk show type thing. This is where I'll be talking about all of my math and physics related things, as in problems and or definitions of how things or how I explain things to better help you guys to understand. So for this video, I will be talking about line integrals. Now this didn't come up, from me. Quite a surprise, yes. But this actually came from a good friend of mine. She came up to me and asked, hey, can you do a video about line integrals? I'm like, yeah, sure. So shouts out to CVD for making this special request. So this is what this video will be about, line integrals. Now, going through all of my books, math, physics books, I saw that this was pretty much a lot to contain into one video. So I'll be making two parts. The first part, this one, will be about just understanding what this line integral, in particular the formula for the line integral, came from and what it's used for. The second one would be about doing actual problems with this formula. So let's get into it. Now the formula for the line integral, which is this guy right here, the integral of f of xy ds is equal to the integral of f of x of t, y of t, multiplied by the square root of dx dt squared plus dy dt squared dt. That's a lot. Now, how these two are equated to each other or the same. The simplest piece is your f of xy and your f of xt yt. Those two are fairly simple. You learned that back in Calculus 2 on how to change a function of two variables to a function of two variables that are not just arbitrary values. They are functions of another variable, in this case time, i.e. the parametric functions. So those two quite simple. Now the other piece, how does the ds equate to the square root of ds or dx dt squared plus dy dt squared dt? Well, we can treat this like an equation. We're going to see where does this come from. So you're going to set both of these equal to each other. And the first thing you notice that these are derivatives, ds, dx dt, dy dt, dt, all the above. Now, what do we do with derivatives besides setting them equal to 0 and solve for a certain variable? Yes, we integrate them, and this is what we'll be doing, integrating. Since line integrals is what we'll be doing, let's integrate. So we're going to integrate both sides. The integral of ds is equal to the integral of all that other stuff. Got it? Good. So the next thing I'm going to do is to change ds into s prime, as you see here. Didn't do anything illegal. ds is the same thing as d prime, just like dy is the same thing as y prime. There's nothing illegal going on here. So now I'm going to integrate both sides of my equation. So the integral of s prime becomes just s, and my right side I'm going to leave it as is, just for the time being. Now, looking at all of this, s equal to the integral of the square root of dx dt squared plus dy dt squared dt, that looks kind of familiar. If I go back to Calculus 2 again, go through your mind all of those file cabinets that you haven't used in however long, you notice that this is very similar to the arc length formula. Instead of s, you may see it as L, like this guy here. L is equal to the integral of the square root of dx dt squared plus dy dt squared det. These guys are practically the same. So there was no new thing that mathematicians or physicists discovered and say, hey, this is going to be for our line integrals now to solve for the mass of a wire or electricity, magnetism, forces, and all that good stuff. No, this is stuff that we already know, just derived to look different. Line integrals are best fit for solving these type of problems, as I mentioned earlier. The mass of a wire, electricity and magnetism and forces and all that good stuff. Fluid flows. Yeah. So that's pretty much it. That's what line integrals are. Now, if I were to go back to the integral of f of xy ds, that piece, we say, well, where did that piece come from? That's just a definition. And that definition is this formula here. The integral of f of x y ds is equal to the sum of f of x y delta s. Now that's just a Riemann sum of an initial point evaluated at this function to an nth point going to infinity, multiplied by their respective lengths, or delta s, of this curve. So these delta s are subcurves or subarcs within this entire curve. So you're just multiplying, those two things together and added them all up. That's where your f of xy ds comes from, and integrating them all. So that's just definition. That is the way it is. That was law. So that's pretty much it. So that's your line integrals. Pretty much understanding how did that first formula I showed you guys came about. So that'll wrap it up for this first video, part 1 of the 2-part video. And I'll see you guys in part 2.